In this video, I'd like to go over the work and energy of a particle and hopefully get to the work and energy theorem. But first, I really need to go over what work is and come up with different types of work done by different forces and equations for them that we can use for different problems that we might see. So first, if we look at what work is, and we have this particle right here, and we're going to say this particle is at some point in space, so it has a position vector, let's just call it r, and we have some force that acts on this particle. It acts like this, and this force right here causes our particle to move, and our particle moves from this point to this point. And since it's at a new point, it needs a new displacement vector, and we'll call this new position vector r prime. And the displacement vector that defines its position from point 2 to point 1, we're just going to call dr. So dr is just going to be this displacement vector right here, and it's equal to this r prime minus r. And this force ends up acting at a angle of theta between this position vector, this displacement vector right here, dr, and the force. So the angle between the tails of these two vectors turns out to be theta. Now with this information, we can define what our work is. And our work is going to be equal to this, we're going to call it du, and u is going to stand for the work. And it's going to be equal to the dot product of our force right here. So this is our force vector. And the dot product of that and our displacement vector dr. Now if we know dot product, we know we can write this in a different way. We can write this dot product as our work is equal to the magnitude of our force times the magnitude of our displacement vector, which I'm going to call ds, and times the cosine of theta. And theta is the angle between the tails of these two vectors. Now, this can be thought of as one of two ways, and we can interpret this equation as one of two ways. We can think of it as the displacement in the direction of the force. So in that sense, it's the ds times the cosine of theta. Or we could think of it as the component of force in the direction of the displacement. And that is sort of this f cosine theta ds. And when we think of it this way, we're thinking of, if we break this force into two components, we have this force that acts this way, and we have a force that acts along our direction of displacement, which is this way. And this, when we this component of this force vector is going to be f cosine of theta. Now, the other sort of situation that may come up is if we have this perpendicular vector. So if we have the particle right here, and it moves in this direction. So we have if we have a particle and it moves from here to here, and we have a force that acts completely perpendicular to this this particle. So this is a 90-degree angle. This is f. Again, we'll call this ds. We know that the work done is equal to force times the cosine of theta, and the cosine of theta is the angle between these tail of these two vectors. So we have work, which is equal to F times ds times the cosine of 90, and well, the cosine of 90 is 0. So the work done by this force is equal to 0. Okay, so now I would like to come up and derive different types of expressions and equations that we can use to deal with different types of forces. And the first force I want to talk about is a variable force. And unlike some of the other forces we'll see in a little bit, a variable force isn't going to have that nice sort of equation you can just plug numbers into and get a final answer, because, well, it's variable. And just like the constant accelerations we saw, it really depends on the function that we have. But we can come up with an expression for this. If we know that the particle goes along some finite displacement, and we'll just call this this position right here S2, and this position right here S1. So it goes from point this S1 to S2. We can integrate our expression for work, and we can figure out what our force is. So if we have this du, we're going to integrate it, and we're going to get our work from 1 to 2 is equal to the integral of f times the cosine of theta times ds. And ds means we're going to go from S2 to S1. And this is going to be our final expression for a variable force. The force right here is going to be a function of s, and then we can integrate with respect to s and get our final force. Now, what happens if we have a constant force? So that's the second situation we want to look at. If we have a constant force, we're still going to take this integral from S2 to S1. However, our force is constant. So u from 1 to 2 is going to be equal to f cosine of theta from S2 to S1. And since this is constant, it can come outside our integration. So times ds. Now, this right here, when we do this integration, we're going to have f times the cosine of theta times s, which is evaluated from S2 to S1. And when we input our two bounds and we evaluate this expression from S2 to S1, we're going to get this is equal to our f times the cosine of theta of S2 minus S1. And this is going to be the equation we have for a constant force, this right here. And this right here was the equation we had for a variable force. And you can see it's still sort of the same idea. It's still this integral. So there's two more forces I want to come up with expressions for, and the first one is our weight. And with weight, we sort of need to think about what weight is doing. So if we have this particle right here, and it has a weight going directly down, it's going to have a weight that's only in the minus j direction. So if we have a particle that goes from this position R1 to a position R2, and this displacement vector dr can be equal to some displacement in the x direction plus some displacement in the y direction plus some displacement in the z direction. If we take a look at this equation right here, we're going to have our work is equal to the dot product of our force times our displacement vector. And if we integrate both sides, we're going to get the work from 1 to 2 is equal to our force, which is equal to minus Wj times the dot product of this displacement. So dxi plus dyj plus dzk. And here's where some of the simplification comes in. A j dot an I vector is going to be 0 because these vectors are perpendicular to each other. We have an I vector right here, we have a j vector right here, and we can even add in the k vector. And we know that all this coordinate system, they're all perpendicular to each other. So the cosine of the angle between them is 90. So j dot product with an I is just 0. J has a j. This one will stay because they're both j components, and this k component right here is also going to be a 0. So when we get this integral, and it's from this R1 to this R2, we can simplify this, and it becomes the integral of just the y's, because that's all that's changing. So y2 to y1 of minus w times this dy. So this dy is what we take this integral with respect to. And when we do that, we get this is equal to minus w y evaluated from y2 to y1. And this is going to be equal to minus w times y2 minus y1. And this is essentially delta y, and that's our difference in height. So our weight only does work if the height changes, and they can do positive work if the height gets higher, because that's what this minus sign's for. But if our the height goes lower and this delta y is a negative, so if we move downwards, this negative delta y right here is going to make it positive. So it can do negative or positive work. All right, so the last force I want to talk about is the force of spring. And with a spring force, let's first look at the springs we're talking about. So we're using compression and extension springs. And if we have a spring that's at an unstretched position, and it's at a position of S1, we can either apply a force that compresses it, and if we compress it, we're going to make it smaller. So right here, we're going to have a force like this, and this position right here is S2. Or we could have a force that elongates and stretches the spring. And if we do that, imagine this the squiggly part goes all the way out, but we have a force on it that acts this way, and this position right here is also going to be S2. So it doesn't matter if we compress the spring or if we elongate the spring, because the force and the displacement, this displacement right here and this displacement right here, they're always in the same direction of the force. So the force on the spring is positive. And if we take a look at this equation right here, and we do what we did with the other types of forces, we integrate both sides. So we're going to have the spring force U1 to 2 is going to be equal to the distance the spring is stretched times the force on the spring times the displacement of the spring. And we know the force of a spring. We know that the force of a spring is equal to Ks. So if we substitute this in to the equation right here, we get the integral from S2 to S1 of Ks ds is equal to the work. And when we take this integral, we have this s term, we're taking the integral with respect to s, then we get Ks squared over 2, evaluated from S2 to S1. Sort of mix these bounds up a little right here. So this is from S2 to S1. This is going to be equal to 1/2 K times S2 squared minus 1/2 K times S1 squared. However, think about this. If we have a particle that's right here on the end of the spring's going to want to pull it back. So we got to account for this in our energy equation, our work equation, by introducing a minus sign. So what happens is the force will do negative work on this particle. So as the particle wants to come further out this way, the spring force is acting against it and wants to bring it back towards its uncompressed location. So that's why we need this minus sign right here.